So now we are going to move on to the discussion time where we can take questions and have discussion on each of the 10 presentations that were given. There have been some questions that have been put in the chat and have been answered by the speakers already. Do we have any new questions that anybody would like to pose for our speakers?
Yeah, so I think if you had a question in the chat that was earlier and you didn't get it answered at that time, just throw it in there again so that we can see it. And also feel free to raise your hand and ask the question in person.
Great, so I see Shuai Li has his hand raised.
Yeah, I have a question for Carl. So like, have you considered like if we use like a radiated trans model, like a Hapkin model, to convert like those reflectance to single scattering albedo and then calculate the band depth? Will that help to reduce or remove the effects of ring geometry? Like you're thinking, you know,
you would be more the expert.
Well, I think I can.
Yeah, so you'd be more the expert at that than I would be, Shuai. I think what approach we're taking is simply to use models from, how's it, Bohr and Huffman. I can't remember which text we're using. Dave Blewett has found some models he can use to calculate the Hapkin reflectance based off of coated spheres. And so it's going to be actually two models of a coated sphere underlain by basically plain old spheres that don't have any OH in them. So that's the approach we're taking. I'm not sure if it makes sense to use an SPAT approach, if that's what you're talking about, to derive abundance, if we're basing that on a model that does not assume coated spheres. But again, I'm relying on the model expert, Dave Blewett, to do that for me, and your insights would be great as well.
Okay, yeah, well, I think what I've done is just intermittent mixing. Yeah, I think trying to use like a different layer and I see how it goes. Yeah, that's a good point.
Okay.
All right, I see another question in the chat from Kevin DePriest to everyone. That is the lunar atmosphere pressure being considered? The pressure of this small mass is around 310 to the negative 15 ATM, varying throughout the day, and in total mass less than 10 metric tons. Is that enough to affect these results? So basically, is the exosphere being considered in these measurements that everybody's been making of the 3 micron region, which I think is an interesting point. Any takers? I mean, as a spectroscopist and the uncertainties associated with the spectroscopy, I mean, I can take a stab at this. I think that the exosphere is just, you know, it's such a low concentration of molecules. You know, spectroscopically, when you're looking at lunar, you know, at least reflected spectra, there is already an inherent degree of uncertainty in those spectra from the spacecraft, the surface roughness, et cetera, et cetera, et cetera. And I don't know, this is just my educated guess, because I don't really do a lot of exosphere stuff, but I think that the influence from the exosphere to a spectra in that context would just be so tiny that it would be overwhelmed by the already existing uncertainty associated with the measurement. And people, feel free to jump in if you have thoughts on that.
I see a comment from Paul Lucy in the chat. Do you want to speak to your comment, Paul?
Oh, I was just referring to a couple of comments before about the band depths, but Yuri Skiratov and Ludmila Starkina showed that just from doing modeling, you get stronger band depths in brighter material, i.e. Highlands. So we need to throw in composition and space weathering as a modulator on the 3 micron band abundance.
Yeah, absolutely. Yeah, I think that, you know, considering the effective composition on all these measurements is, I mean, I'm biased towards my own research, but I think that is a very important next step, because I can already see in my studies of like the specifics of the 3 micron region, the way the shape and intensity of that feature looks and changes is very different on the basis of what mineral or material you're looking at, because they all have, you know, different structures. You end up with different bonding environments. So yeah, I think that that's an important point to make.
Absolutely. Darby Dyer would agree with that. She has demonstrated, she makes measurements that has in the past, along with her previous advisor, I forget the fellow's name, in the mid-'80s, published on the different absorption constant strengths, absorption strengths for water and different minerals. There's definitely an effect. It's not a factor of 5 or 6, but you know, it's an effect that needs to be considered. Also, the position of the band changes significantly. So the identification of water by the position of H2O by the position of the 3 micron band may not be accurate if you're looking at anorthite material, which tends to have a OH feature that shows at longer wavelengths than in more mafic minerals.
Yeah, exactly.
I have a question for the presentation of water looking during eclipse. Was potential effect of absorption by water in the Earth's atmosphere of sunlight, you know, during the lunar eclipse considered? The light from the sun, I believe, be passing through the Earth's atmosphere that contains water. Could that have induced a 3 micron band in the apparent reflection spectrum from the moon's surface? That was Jessica, I think, who presented, if I remember the name correctly.
That was Abby, but
Abby,
I'm not
sorry.
sure if she's around still, so I can try and address that a little bit because we, you know, work on the same data. When we observe on the IRTF, we take spectra of a solar analog star to hopefully remove some of the atmospheric water in the band. But under eclipse, the observing conditions are quite a bit different. But in theory, we are attempting to remove almost all the atmospheric absorptions as much as we possibly can. So we are seeing mostly the water that's on the surface. And also the atmospheric water is in more of a gaseous phase versus like on a solid surface. So I'm not sure what that would look like in our 3 micron band in our IRTF observations. I think that would look very different for us. Maybe Paul has something to say on that if he wants to jump in too.
Yeah, I think what Carl's saying is the light from the Earth reflected off the lunar surface, not the atmospheric effect. So, Carl, we've measured the reflectance of the moon during total eclipse, and it's almost 100 times fainter than the reflected signal we get from the direct illumination, even during partial eclipse. So, we haven't actually corrected for it, but it's going to be small, and it doesn't show a real obvious water band. We're actually kind of disappointed in that.
I bet. I was actually thinking of the light in the penumbra, whatever, that would contain some sunlight that was absorbed by water in the atmosphere before it actually reflects off the surface of the moon.
Oh, like an exoplanet atmosphere.
Yes, exactly.
Yeah, you do see this in total eclipse, and you see beautiful atmospheric features short of 2.5 microns. For whatever reason, it's flat as a pancake in the 3 micron region.
Interesting. Yeah. Thank you.
All right. I think that we've got a good comment in the chat, and then I'm considering posing a question to the group. So Tom Orlando has pointed out that some folks mentioned OH migration. I want to point out that this happens via proton hopping, and the center of mass of O is not moving. The relative concentrations of OH at the surface ends up changing, the survival of these are very temperature dependent. They end up making some water that can leave. I think that's a really good point. And Tom, correct me if I'm wrong, but didn't you and was it, oh my goodness, how am I forgetting her name? My brain is fried. Didn't you have a paper that you were a co-author on that particular subject relatively recently?
Brant Jones is the primary author on this. We had a couple of papers on this, and then we also related it to mercury.
Okay.
Yes, actually. And if Brant is tied in, he could comment on this. It turns out if you apply this model, it maps out exactly what Casey was showing in terms of the latitude and temperature dependence of the 3 micron band. Their data is very well reproduced by the model. Brant is actually the primary modeler. And if he's on, he could chime in, but he's the person to talk to for the modeling.
Mm-hmm.
Let me jump in though. The magnitude of the change that we were on, I was on that paper too, was small compared to the magnitude of the change inferred from the variation in the IR band. So while the distribution is very well matched, the magnitude is not by as much as an order of magnitude. And
that's with regard to that's with regard to the magnitude changes from Shawlee's paper and MCube data. But if you look at some of the slope changes and things that Casey was showing, I think it matches better.
Yeah,
and
I talked.
it did match. It did match the 0.1% monolayer thickness from the Hendricks paper.
Yes, exactly. That I presented that.
Yeah.
Matches UV stuff well. Doesn't account for the larger IR difference. And I just want to point out it. In Micah's paper, he references 2014 paper with Gradiola. It looks like that absorption band for that it takes equivalent of over 3 years of proton irradiation to create that size absorption band if that were on the moon. And so I want to bring this up that we need to consider fluence and flux as well as total abundances and things of that nature. And I think we have a fundamental issue in terms of solar wind not being a high enough flux to account for a diurnal variation. I won't rehash my presentation.
Okay. Thank you, Carl. We have another question in the chat, and then we also have a hand that's raised. So I'm going to first go with Parvathi's question to Alice. Do you have thoughts on what sort of measurements or samples would help in further understanding the contribution of nebular hydrogen to the Earth-Moon system? It seems like that might be the oldest flavor of lunar volatiles. So I'll hand that over to Alice.
Yes, sorry. Yes, so I think the sample we are trying to look for is the one that are supposed to be the most primitive into the lunar mantle. So the one that are mostly island materials like the norite, because at the end we have one sample that has the lowest delta D value, from which is at the bottom of the degassing trend, but we need a bit more sample to make sure this value is really recorded in other samples too. I don't know if that makes sense. So.
That was an excellent question, and thank you, Alice. So, OJ, I see you have your hand up.
Yeah, this is more so of a comment. I just sort of like to advertise a paper we did in 2018 where we looked at the diffusion of hydrogen using an activation, a distribution of activation energies. And, we were able to obtain a good agreement in abundance and the latitudinal dependence consistent with Shawlee's results. So, please take a look at that paper too. And we also have a more recent one looking at how it changes when in the magnetotail, 2021.
That sounds fabulous. If you could link those in the chat, that would be great so that people can grab the citation and take a look at those. All right. Well, I want to pose a little group thinking exercise to the group, since I don't see any hands up, or I think that OJ, you have a what was it called? Somebody had a funny turn of phrase for this. You have like an old hand up. But I'm wondering if any, like, we've just talked about a lot of potential influences on this lunar hydrogen cycle that we're observing, you know, surface roughness, temperature, sun angle, et cetera, et cetera, et cetera. If you had to sort of pick one arena that you think would be the most important to move forward in terms of better understanding the lunar hydrogen cycle, I guess, what do you think it would be and why? And if we want to take 30 seconds or a minute and have people post their answer in the chat, I think that could be fun. Kathy, I don't know what you think.
Yeah, I like that idea.
Okay, yeah.
It'd be interesting to see what people come up with.
What's your takeaway here?
Yeah. So while we're waiting for people to put questions in or to put their thoughts in the chat, I have a question for Pedro. Have you considered any work of doing comparisons of your research with the maps and the data from LRO that is available? Pedro's still on.
Here's Pedro is not still on.
We have lost Pedro. Okay,
Oh,
I will have to
no.
visit the
Oh, wait.
poster.
Kathy.
Okay.
Is that?
Yeah. Oh,
Yeah, this is
Pedro?
Toshi. Yeah, I'm working with him.
Okay.
So yeah, I'm working with him. Regarding your question, that's a good point. We are currently working on that. Definitely. So the major part of his work is like trying to understand the mixing depth and the correlation with ice content concentration rate. Definitely like using data, and especially LRO would be really important. So yeah, he's currently working on that. Thank you for your question.
That's great, and I would welcome him to get in touch with team members from LRO, because we'd be very happy to help him with understanding any of the data products that we have. We love
Sounds
having
good.
everybody use our data.
That's great. Thank you.
So we now have a stream of comments coming in. And
A+ on class
Elizabeth.
participation, guys.
Yeah, yes. I see Elizabeth frantically making notes.
It's usually worth 10% of the grade.
Yeah. But I mean, what's the saying that, you know, 50% of the effort when you're doing something is just showing up? So I know I'll count it higher, and you know, I'll weight it higher for the overall grade I will give this this group. Okay.
Yeah. Very
So
good comments.
you just want let's start taking a look at some of these. What do you think, Kathy? Should I just read them?
Yeah, that sounds good. So it starts with Paul.
Yeah. All right. So Paul started us off with laser reflectance at 3 microns, global night and day. And I personally am very biased towards that, of course, because I did laser reflectance and had a rollicking good time looking in the PSRs. So, and yeah, if people have comments or thoughts on this, yeah, just throw your hand up and we can discuss more. Casey Seconds laser reflectance. Oh, Jeff asked you to put the question in the chat and I didn't. I'm very sorry. Jeff, if you're still here, I hope you were able to participate despite me not seeing that comment. All right. Carl has more observations, especially bidirectional reflectance of the lunar surface from orbit and ground, including microscopic imaging at 3 microns. That's fun. Of just like soil or regolith grains, Carl? You know, just doing.
Yes. Oh, the regolith, both disturbed and undisturbed. Because from landed, if you look at the disturbed soil, you might actually see what pristine soil looks like, or even look at the hopping of water across that from the plume material. It could be your own experiment for, you know, water absorption, desorption from a landed experiment.
Oh, for like a lander.
For a lander, yeah, right. That could be really interesting about understanding the migration of H2O or adsorption as OH. But from orbit, I'd really like to resolve this whole idea we have of incidence angle dependency. But I like the laser stuff, especially with PSRs. How else are you going to measure it in PSRs without active illumination?
Yeah, absolutely.
There is a problem with the photometry at 3 microns, is that it's still a mixed reflected thermal emission signal. So you can't do like we do at shorter wavelengths. You need to solve that problem before you can solve that problem.
Yep, and Abigail Flom actually said that as well, as like what she thought the most important thing would be for moving forward here. I think that's a great point.
Yeah, that's also partially because Paul and I are going to do some lab experiments to take a look into that problem. So.
Oh, so you're coordinating.
It's on the mind.
Gotcha. Yeah. Well, I can tell you, I agree strongly.
Yeah.
For the 3 micron measurements in illuminated terrain, because the water is relatively stable, as long as you have a good thermal correction, then you should be able to accurately measure the shape of the band. It should not be dependent on the temperature of the grains, because those grains are going to see all the various temperatures at some time of day. So you should be able to see some average band. It's not like in the PSR, where if you're looking at, it's very different.
Absolutely. I do think, though, I'll make a short comment on the photometry, as from the perspective of someone who's been trying to do radiative transfer modeling in this region. I can barely get away with it because we're at Earth-like temperatures in the lab. If you heat that up at all, you start having, thermal influence, but the assumptions that you're making about the physics of how light is interacting with particles in that region also begins to change. You start getting into this crossover region, which in terms of like understanding like the actual radiative transfer processes and like how it's playing out in there, it's still kind of the Wild West. My office mate, Chris Kramer, works on it, and we have a lot of discussions about what the heck might be going on.
You have emission, emissivity, you have to separate temperature, emissivity separation is a big.
Yeah. So from a modeling perspective, that region is still kind of a nightmare. So yeah, I think that's a great point. So we have from Laszlo that nitrogen is important to measure, but photometry is a pain and you can't ignore it. Oh, yep. Laszlo also agrees. I think we're sensing a trend here. OJ Tucker has temporal variation of hydrogen in the exosphere to constrain chemical formation rates in the regolith. And yeah, I don't know if anyone can speak more to that, who knows more about exospheres.
Yeah, we had the Laddie presentation on each. That was by Kate or Kari. Is Kari still on?
Everybody left.
I think Laddie is the best bet for measuring H2 because of in situ. With LAMP, we measure the exosphere, but I'm not too sure how many H2 measurements we've got.
Right. I mean, LAMP. Right. So, so far, LAMP hasn't been able to extract like the diurnal variation. They looked at the morning and evening terminators, and Chase did like a short measurement while in the magnetotail. So really all we have is LADI right now of H2. And, you know, as Kaya talked about, it's really difficult to sort of extract the H2 densities from LADI because just so much noise. So, but I think, you know, in the future, if we can, you know, really get an idea of how it varies temporarily, then we can understand better the solar wind contribution to H2, forming H2 and other hydrogenated species in the regolith to sort of help constrain some of these ideas.
So the current state is that it's really hard to measure and we don't have enough information, basically. Yep. Ari, do you have anything you'd like to add? I see that you're still on.
Perhaps.
You are muted. Yeah. Okay.
All right. I just realized that in my excitement to say that a lot of people agreed with the photometry point, like how that's a pain and we really need to figure that out before we proceed, I skipped over Shuai. I'm sorry, Shuai. Shuai said that regarding the fact that most OH H2O could be concentrated in grain rims in the top tens of nanometers, diffusion of H could be significant at relatively high temperatures, such as above 350 Kelvin. Yeah. Shuai, do you want to expand at all, or?
Yeah, so this is like what I got from OJ and also from Bill's work about the diffusion. And also I did something like modeling work. I feel like because as we know, the solar wind implementation only occurs like on the top, like maybe up to 20 to 50 nanometer on the surface. And at least has been demonstrated with Apollo samples. So like that's so thin layer, right? Nanometer, 10th nanometer. So I'm thinking like a hydrogen can be very mobile at like a relatively high temperature. It can just move around. Because, you know, once the hydrogen moves away from oxygen, you won't see any OH feature. So that means like, you know, as the temperature changes, like the H moves around, and also you will observe the OH feature change.
Yeah. Yeah.
Yeah. So I saw Tom also had a comments on it. So I'm not sure Tom wants to explain more about what his thoughts.
Yeah, and I'd just like to mention really quick that further down in the chat, great minds think alike. Pavarthi also was talking about how she'd be really interested in understanding the physical form of H on the surface, how much is migrating, locked up in rocks, etc. Agnostic on method. But yeah, I think that this kind of speaks to a larger trend that I've noticed, that it's like we tend to get stuck talking about water, but it's been really helpful for myself to reframe this as like we're looking at a hydrogen cycle, like, and you know, taking a step back and thinking about how hydrogen is behaving in the environment and how, you know, sometimes that might result in hydroxyl in water and sometimes it might not. And considering,
so we have reached the point of transition to plenary, and I think our channel is the one that is used for the plenary.
Okay, yeah.
So
I thought we had, oh, we're at the end.
Discussion, yes.
Oh dear, I'm sorry, I feel bad that I was talking.
That's okay.
Yikes.
So we want to thank everyone who participated in this session. It was really great presentations and wonderful discussion afterwards. And I think we've got a 5-minute transition now to the plenary that's coming up on the PRISM payload suites panel. So I want to thank everybody for coming. Yeah. And thank you, Elizabeth. Do you have anything, last words?
I hope it was
You've done an amazing job. Yes.
Yeah, but this was really fun, guys. Thanks so much, and thanks for participating. I hope you guys had a good time as well.